hope you have had a chance to view my videos that introduce the fundamentals of chemistry. Batteries and fuel cells are practical applications of chemistry. A battery is a store of electrochemical energy. A fuel cell is a battery in which the chemicals can be continuously restored with new chemical fuel. Once the chemicals in a battery are depleted, the battery must be recharged or discarded. Some batteries are easily recharged. In some batteries, the electrochemical reaction is one way and recharging is not practical. Fuel cells also have an end of life where components degrade to a point where adding new fuel is impractical. Batteries can be built that are small enough to power a wristwatch. Fuel cells require external piping and fuel tanks, so the smallest fuel systems that are available are used in golf carts or forklifts. Small fuel cell systems have been developed to control galvanic corrosion of pipelines that derive their fuel straight from the chemicals pumped through the pipeline. Terminology is similar for both batteries and fuel cells. Both produce direct current or DC electricity. Both have anodes and cathodes. Both have positive and negative terminals. Both have an electrolyte or similar permeable barrier that keeps the anode and cathode chemicals separate. The barrier forces the electrons to travel the circuit. The permeable barrier permits the ions to migrate between the anode and the cathode side. Both are called cells, and both batteries and fuel cells have half-cell reactions that occur on the anode and cathode halves of the cell. DC current can be converted to alternating current, or AC, by means of power inverters that may contain switches, capacitors, inductors, and filters to reverse the current direction and moderate and smooth the AC electrical signal. The convention for electrical current is opposite to the flow direction of the electrons. The convention for electrical current direction was established before electrons were discovered. The 18th century scientists had a 50-50 shot at guessing whether charge carriers would be positively charged or negatively charged, and they guessed exactly wrong. They guessed the charge carriers would have a positive charge. When negatively charged electrons were isolated as the charge carriers in the 1890s, all the books had electrical current traveling in the wrong direction. This mistake has never been corrected. So when you see the electrical current direction on a circuit, the current direction is opposite to the direction of the electrons' travel. The terminals on a battery are where the wire circuit begins and ends or terminates. The cathode is on the positive side of the battery. The anode is on the negative side of the battery. The cathode terminal or positive terminal is where the current leaves the battery. The anode terminal or negative terminal is where the current enters the battery. In reality, the electrons leave the anode or negative terminal and travel towards and enter the cathode or positive terminal. To understand how a battery works, it might be easiest to describe the operation of a wet cell or galvanic cell with a zinc anode and a copper cathode. The zinc-copper wet cell is divided in half by a porous disc that is permeable to ion flow. The electrolyte is the aqueous copper sulfate solution in the cathode half cell and the aqueous zinc sulfate solution in the anode half cell. Zinc is 1.1 volts more electropositive than copper. When the wire is connected between the two electrode terminals, the electrons will be driven from the zinc anode into the copper cathode. The electrons are coming from the anode half cell reaction. Zinc solid plus sulfate ions react into zinc sulfate plus 2 electrons. At the surface of the zinc anode, the zinc in contact with the sulfate ions in the electrolyte solution dissolve into zinc ions Zn2+. The zinc sulfate solution becomes more positively charged and attracts anions or SO4 ions from the cathode half cell through the porous disc and into the anode half cell. The electrons follow the wire circuit through the light bulb and into the copper cathode. The copper cathode becomes more negatively charged, so the copper ions, CO2 positive, are deposited onto the copper cathode surface. Essentially, the copper cathode is becoming electroplated with more copper as the zinc anode is being dissolved. The cathode half-cell reaction is as follows. 2 electrons plus CuSO4 aqueous react into Cu solid plus SO4 2 negative. The cathode half-cell is being reduced in charge. At the same time, the zinc anode is being oxidized by the incoming SO4 ions, converting the zinc into dissolved zinc sulfate. The voltage across the terminals is 1.1 volts. The electrons will continue to flow until either the zinc anode dissolves completely or all the copper sulfate is used up. The galvanic cell is named after Luigi Galvani. In 1780, Galvani discovered that when copper and zinc are pressed at opposite ends of a severed frog's leg, the muscle contracts as if it were alive. Galvani published his discovery in 1790. Alessandro Volta read Galvani's paper and thought that two different metals Galvani used were more important than the medium, the frog's leg. In 1799, Alessandro Volta constructed the first battery, the voltaic pile, by inserting a piece of cardboard between discs of copper and zinc. When the cardboard is wetted by salt water, it acts as an electrolyte. The electric current will pass through the wire connecting the copper to the zinc. Our unit for electromotive force, the volt, is named for Alessandro Volta. In the figures I show the voltage difference between various metals compared to copper. Note that zinc is 1.1 volts more electropositive than copper. A more familiar wet cell is the lead-acid battery used to start cars. The lead-acid wet cell is similar to the zinc-copper wet cell, except in the lead-acid wet cell, the anode is lead, the cathode is lead oxide, PbO2. The electrolyte is battery acid, aqueous sulfuric acid, or H2SO4 solution. There is a 1.8 to 2.1 volt potential difference between the lead anode and the PbO2 cathode. When the wire is connected between the two electrode terminals, the electrons will be driven from the lead anode to the lead oxide cathode. The electrons are coming from the anode half-cell reaction. Pb solid plus HSO4 aqueous reacts to form PbSO4 solid plus H plus 2 electrons. At the surface of the lead anode, the lead reacts with the hydrogen sulfate ions in the electrolyte solution and begin depositing on the anode as solid lead sulfate. H plus ions are released into the solution, and the electrons follow the wire circuit through the light bulb resistor and into the lead oxide cathode. On the lead oxide cathode side, the incoming electrons trigger the PbO2 to break up into Pb2 plus 2 oxygen 2 negative ions. In the free lead ions, Pb2 plus immediately reacts with the free sulfate SO4 2 negative to become PbSO4 solid. This solid deposits on the lead sulfate cathode. The 4H plus ions bond with the free oxygen ions to become 2H2O water molecules. The cathode half-cell reaction is 2 electrons plus PbO2 solid plus HSO4 aqueous plus 3 protons aqueous reacts to form PbSO4 solid plus 2H2O liquid. When the cathode half-cell reaction is broken down fully, you should see that the 2 electrons went into breaking up the lead oxide into lead ions and oxygen ions. The cathode half reaction is balanced in both elements and charge. The open circuit voltage across the terminals is between 1.8 volts and 2.1 volts. The electrons will continue to flow until the circuit is broken or until the anode and cathode are fully converted into PbSO4 or the sulfuric acid becomes too dilute to continue the process. In a 12-volt car battery, there is more than one cell. The lead and lead oxide electrodes are put into the battery in rows of square plates with a porous plastic or fiberglass separator sandwiched between them. Each pair of lead and lead oxide plates is a cell. 7 plate pairs or 7 cells may be wired together in series and placed in a single 12-volt battery. With cells in series, each cell adds its own voltage difference to the total voltage across the battery terminals. The total open circuit voltage across the car battery terminals may be between 12.6 and 14.5 volts. A 12-volt car battery may put out an initial current of between 600 amps and 1000 amps to crank the starter. A 12-volt car battery might store between 2.75 amp hours per kilogram or 1.25 amp hours per pound. So if the car battery weighs 40 pounds or 18 kilograms, it could store 50 amp hours of energy at 12 volts. Energy equals volts times amps multiplied by time, So to convert to watt hours, simply multiply the 12 volts to get 600 watt hours. 600 watt hours times 3600 seconds per hour equals 2,160,000 watt seconds. 1 watt second equals 1 joule, so we have 2,160,000 joules, or 2.16 megajoules of energy. So a typical 40-pound car battery might contain 2 million joules of energy. Of course, a regular car battery is not meant to discharge all of its stored energy. Every discharge plus recharge is a cycle. Some lead sulfate does not get restored back to pure lead. Car batteries might last several thousand cycles if the discharge is less than 10% of their power between recharges. Starting a car should only take a few seconds of discharge. Once the engine is running, the alternator or generator is spun by the engine, and the battery immediately begins to recharge. Deep cycle lead acid batteries are built with thicker lead plates and can discharge up to 50% of their power between recharges. Deep cycle batteries are better for running electric trolling motors for a boat or for storing solar power for use during nighttime hours. And that concludes my discussion of wet cell batteries. In my next video, I will focus on dry cells, namely alkaline and lithium-ion batteries. Alkaline batteries are the flashlight batteries or smoke detector batteries found around most homes. Lithium-ion batteries power cell phones, laptop computers, and many electric vehicles. Thank you for watching. If you enjoyed this video and want to help me make similar content, please like and subscribe.